So I guess you know the midterm is marked. If you haven't already, you can see your marks on Moodle. And then above, I pasted a histogram of the distributions of the marks. So if you fall on the bottom side of that histogram, then you need to be studying more. Okay. Are there any questions about the midterm? That's just the grade on the midterm. The overall grade would depend on how many assignments you handed in, etc. Okay, so no questions? All right, in that case, we'll get started on Chapter 5, which deals with conservation laws and symmetries. It's a relatively short chapter. Oops. But I think it's quite interesting. So we already looked into this topic a little bit last chapter when we dealt with cyclic coordinates. And we saw that when a coordinate is cyclic, so when the Lagrangian doesn't depend on that coordinate, then the conjugate momentum associated with that coordinate is a conserved quantity. So that's sort of one conservation law that we've already established. And another one was when the Lagrangian doesn't depend explicitly on time, then we saw that the Jacobi integral was conserved. And in most cases, we saw that the Jacobi integral is indeed the total energy. And so we concluded that when the Lagrangian doesn't depend explicitly on time, then the total energy is conserved. So we already had our conservation of energy and momentum come out of considerations of what the Lagrangian depends on. In this chapter, we formalize that a little bit into saying that if the Lagrangian is invariant to some symmetry, then there must exist a conserved quantity. And that statement is called Noether's theorem, named after Emmy Noether. She was a physicist in the early 1900s. Actually, last week was her, 115th birthday or something. There was the Google Doodle was dedicated to her. She has an interesting life, and it's worth reading about her. She was a peer with Albert Einstein, who had a lot of appreciation for her. That's one of her big works, was to figure out the very general connection between symmetries and conservation laws. So let's just recall what we found for cyclic coordinates and generalized momenta. So let's look at conserved generalized momenta. Let me remove this box. Oh, no, we're going to have some palette problems here. No. so let's look at the generalized momenta. So recall the definition of a generalized momentum. Pi is defined to be di-L by di-Qi dot. That is the generalized momentum P, I, that is conjugate to the coordinate Qi. Alright, so you can always choose a Qi and find its velocity, Qi dot, and do di-L by di-that, and you'll get what we call the generalized momentum for that coordinate. Now if you look at the Euler-Lagrange equation, we have d by dt of di-L by di-Qi dot. That is d by dt of pi, right? Minus di-L by di-Qi equals to 0. So if Qi is cyclic, that means that di-L by di-Qi is equal to 0. Then we have d by dt of pi, because the thing in parentheses above there, di-L by di-Qi dot, is pi. So d by dt of pi is equal to 0. And when d by dt of something is equal to 0, we say that thing is conserved, because that thing is constant as a function of time, right? And I can write the equation above just using our different notation that pi dot is equal to 0. That's just saying the same thing, right? D by dt of pi. Sorry, this little gray box is really bugging me. Let me take 30 seconds to get rid of it. Yeah, I feel like it's crashed. Hopefully that's not going to make the computer reboot itself. Alright. Okay, so we have a Lagrangian. We can look at a Lagrangian and see which coordinates are cyclic, because they literally don't appear in the Lagrangian. And then we can write out this conserved quantity pi. So that's a really powerful way of finding things that are conserved. So let's do an example. This is something we've done before. Finding conserved momenta in a Lagrangian. We'll use a Lagrangian for a particle subject to a central force. So an example of a central force is gravity, or the Coulomb force, right? Things that depend is 1 over r squared and that point towards the center. That's what I mean by a central force. And gravity, Coulomb force. Okay, that's example 5.1. So the Lagrangian for that in Cartesian coordinates the Lagrangian for a particle in a central force, L, it's T minus V, so it's a half m x dot squared plus y dot squared plus z dot squared, and then minus V, well V, the central potential, depends on the distance to the origin. And so I'm just going to say that, I'm not going to write out explicitly what the function is, I'm just going to say it depends on the square root of x squared plus y squared plus z squared. Everybody agrees that that's, we have to have, at the origin, a big mass, and then your point mass is out here, and so the distance r equals to the square root. So in Cartesian coordinates, there are no cyclic coordinates, right? So there are no conserved momenta, or generalized momenta. Now let's do it in polar, or spherical, what did I say in a minute? Spherical. Spherical coordinates. And the Lagrangian is again T minus V. So the Lagrangian in the kinetic energy in spherical coordinates, you know how to find that. It was in one of the assignments. So I can take that as given. In spherical coordinates, the kinetic energy is r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. Now the potential, because we're in spherical coordinates, it really only depends on the radial coordinate. So that'll be an obvious reason why you choose spherical coordinates, is because the potential energy is much easier to write down. So we have three generalized coordinates, right? Just like in Cartesian coordinates, we clearly still have the same number of degrees of freedom. We need the same number of numbers to describe the system. So our three coordinates are r, theta, and phi. So in spherical coordinates, let's look for cyclic coordinates. So is r cyclic? R is not cyclic because the second term of the kinetic energy has an r in it. So the generalized momenta associated with r is not conserved. However, well, let's look at theta. Theta is also not cyclic, right? Because it's sine theta. I think it's sine squared theta. The square of the So theta is not cyclic either. So what about phi? Well, if you look at phi, phi is cyclic. The only phi that appears in the Lagrangian is a phi dot, but phi itself does not appear. So just by choosing a different coordinate system, we find that there is a cyclic coordinate, and that cyclic coordinate is phi. So if there is a cyclic coordinate, then the generalized momentum associated with that coordinate is constant. So p phi, which is defined to be di-L by di-phi dot. So if I do that derivative, it's the derivative of the last term of the kinetic energy. So I just get m r squared sine squared theta phi dot. And that is conserved, or it's constant. So you recognize what that conserved quantity is? That is the angular momentum out of the plane of the trajectory of the particle. Okay, so typically that would be the total angular momentum. Alright, but that's not what's interesting. What's interesting here is, well, it is interesting that we found the conservation of angular momentum. So we just have a system that has spherical symmetry. Actually, it is interesting. And in Cartesian coordinates, we didn't exploit any symmetry of the system, right? By system, I mean the thing that's sketched at the top, right? Some big attractor at the origin, whether it be gravitational or electrical, and then some free particle. So in Cartesian coordinates, we don't exploit that symmetry at all. We don't find any conserved quantities. In Cartesian coordinates, the generalized momenta are going to be linear momenta, right? It's going to be mx dot, my dot, and mz dot. In Cartesian coordinates, we don't expect any of those to be conserved anyway. In spherical coordinates, though, We do expect angular momentum to be conserved in the system, and so indeed we find that it is. But it's a little bit disturbing that in Cartesian coordinates we completely missed conservation of angular momentum. Okay, so maybe we don't need it to solve for the problem, but it would be nice if we just had a rule that tells us here's how you find all the things that are conserved. And clearly it looks like it depends on our choice of coordinate system. So in the last chapter of that we'll probably do in the course, I think that's chapter 8 on canonical transformations, we will look at a procedure that gives us a coordinate system where every single coordinate is cyclic. So that's easy, right? Because then every single coordinate is cyclic, so every coordinate has an associated conserved generalized momentum. And so it's easy to solve for the equations in motion if the momentum is constant. So we will find a way where we can transform the Lagrangian to a new coordinate system where all the coordinates are cyclic. And then the system is solved trivially. So the tricky part in that will be finding the transformation of the coordinates. So we've actually just changed our focus of where we do the work. Either we do the work in solving the equations of motion, or we do the work in deriving the equations of motion. So in the system where all coordinates are cyclic, all our work is in finding the correct transformation. So in this chapter, we look at a more general way of just identifying quantities that are conserved without having to find a magical coordinate system that gives them to us. All right, so the goal of this example was just to show you that we want to get rid of this arbitrariness of the choice of coordinate system when we want to find conserved quantities. Because conserved quantities are good and make things easier. All right, so that being said, we need to understand a little bit about continuous transformations. Because Noether's theorem is going to tell us that something about symmetries under continuous transformations lead to conserved quantities. So we need to know what a continuous transformation is. So let's consider a transformation of coordinates. So we'll go from a system Qi and T, we allow for T to transform as well, to a new coordinate system Qi primed and T primed. This is a new coordinate system where time is measured with a different kind of clock, and position, a different kind of meter stick, and could be actually different. So a continuous transformation is a transformation that depends on a single tunable parameter. So if we have a transformation from coordinates Qi to Qi prime and T to T prime, we can write that Qi prime is some function Qi prime of the original coordinates. The original coordinates could be Qi, they could be Qi dots, and they could have T in them. And then T prime is some function T prime of, again, the original coordinates, the original velocities, and the original time. So that's just a general transformation. A contact transformation, as we called it in the previous chapter. So the transformation is continuous if we can write it in the following way. So it's continuous if we can write it in terms of a parameter epsilon that can be varied continuously. So that is that we can write the transformation equation qi prime is equal to qi prime that depends on the qi dot t, and some parameter epsilon that we can make as small or as big as we like. That's what we call a continuous transformation. And then same thing for t. So t prime would be equal to t prime function of the original coordinates and velocities and time, and this parameter that we can tune. So an example of such a transformation is, for example, a translation. So you can have a translation is a continuous transformation because I can tune the amount by which I translate the coordinates. And I can make that amount infinitesimally small. So the whole point of a continuous transformation is that it's a transformation that you can consider in the case when you make an infinitely small transformation. So continuous transformations allow us to consider the case where the transformation is infinitesimal. So, example, translation. What's the example of a coordinate transformation that's not continuous? Because now it sounds like everything's continuous. So rotation is also continuous, right? You can always make the rotation very, very small, by a very, very small angle. And think of a easy-ish transformation that's not continuous. So a reflection through a mirror is a rather straightforward transformation, but it's not continuous. You can't only partially reflect. You either reflect the whole coordinate system or you don't. Okay? So not all easy-looking transformations are continuous. So in the case of a continuous transformation, we can consider an infinitesimal transformation. So thus we can consider the case when epsilon is very small. So when epsilon is very small, qi prime is going to be almost equal to qi, right? Because it's barely even transforming the coordinates. So in that case, we can write that qi prime is equal to qi, the original coordinate, plus a small little change, a variation, which we'll call delta qi. So I'm just going to write that to be explicit. This variation is like a little function that depends on the coordinates. And then it's multiplied by the delta epsilon. So that's equivalent to what we have above here, right? If the transformation is continuous and it's over a very, very small epsilon, so small that we call it delta epsilon, then qi prime is almost equal to qi. It differs by qi by some delta qi. And that delta qi we can write as some function multiplied by our tiny epsilon. And so presumably there's one fi per qi. Right? X and y might transform differently. So we allow for as many functions f as there are degrees of freedom. And then for time, we would do the same thing. We write the time as the original time plus some small change in time. And we write that small change in time as a function g. There's only one time, so I don't need an index on it. And that function g will depend on qi dot t, and it multiplies some small epsilon. Okay, so then to be super explicit, delta qi is fi times delta epsilon, and delta t is g times delta epsilon. Copying out what I have above there. Alright, so that's my thing on continuous transformations. And then we'll do a couple examples now. So the idea is that you can picture a coordinate transformation that's continuous, and so it depends on a small tunable parameter, so you can make the transformation as big or as small as you like. Once you've identified such a transformation, you can write it in terms of this f and the g. So let's figure out what f and g are for like a couple of common transformations. So 5.2, example 5.2. So what are fi and g for, for a translation along the x-axis by a distance epsilon. Okay, so we're looking at translations along the x-axis, and let's consider the non-infinitesimal case to start with of the translation by a distance epsilon. So not infinitesimal. Okay, so for translation, so we have a new coordinate system with primes on it, Cartesian as well, and it's translated from the original coordinate system by a distance epsilon. Well, we can write that x prime in the new system is the original x plus the translation amount. That could be a plus or minus depending which way you translate it. In the new coordinate system, y prime is unchanged, z prime is unchanged, and t prime is unchanged. I guess I could have written that over several lines. Let's make it a little bit neater. So everybody agrees that that is translation by distance epsilon in the x direction. Right, the primes are the new coordinates that are transformed from the original coordinates. Because the translation is only about x, along x, then only x changes. So now that we have the transformation, we can look at the infinitesimal version. The infinitesimal version is you go from epsilon, you go to delta epsilon. Okay, so let's look at this. We have x prime is now going to be equal to x plus delta epsilon, and then y prime is equal to y, so unchanged. Z prime is equal to z, and t prime is equal to t. And remember, what was the goal here? Well, the goal was to figure out what f, I, and g were. So there are three f's, right? There's an fx, an fy, and an fz. And then g, there's only one per time. Now that we've written the transformation in terms of delta epsilon, so we've written the infinitesimal version of the transformation, we'll go back and look at our definition to figure out what fi and g should be. So fi is the part that multiplies delta epsilon. Right, so here I have x prime equals x plus 1 times delta epsilon. Y prime is equal to y plus 0 times epsilon, etc. Right? So here we can figure out that fx is equal to 1, fy is equal to 0, fz is equal to 0, and g is equal to 0. So these have special mathematical names. They're related to the generators of the transformation, but we don't need to worry about that so much. Basically, these are the coefficients that allow us to describe the infinitesimal version of the translation in the x direction. So it's easy to generalize, right? An infinitesimal translation in the y direction has fx equal to 0, fy equals to 1, and all the other ones equal to 0. Okay? It's a bit of an odd way of doing things, but you'll see why, because it helps with method experience. But it shouldn't be too mind-boggling, right? The translation's easy. Let's do the one that's a little bit more involved, at least conceptually. So that's example 5.3. So we want fi and g for a rotation. Let's say it's a rotation about the z-axis. We'll define f and g, which is now write a little bit of a procedure based on what we just did. It seems like step one is to write the transformation in terms of epsilon, which is a non-infinitesimal, that says infinitesimal, and then 2, write the transformation in terms of delta epsilon, and we can just pick out fi and g. Okay, so for rotation, we start by the non-infinitesimal version, right? So we'll do rotation about the z-axis. We'll do by an angle epsilon. And then we'll make epsilon small to delta epsilon and see what happens. So for rotation of a coordinate system about the z-axis, I'm not going to derive this, I'm assuming you know how to do this. The new coordinates, x prime and y prime, are given by the original coordinate, x cosine of epsilon, minus y sine of epsilon. Y prime is given by x sine of epsilon plus y cos of epsilon, and z prime is equal to z, and t prime is equal to t. Right, this is the coordinate system. We have an original coordinate system, x and y, and then we have a rotated system. X prime and y prime, and the rotated system is rotated by an angle epsilon. Alright, so presumably you've done this before. You want to express the coordinates in the prime system in terms of the coordinates in the non-prime system, when there's a rotation by an angle epsilon. The z and t components obviously don't change, but then the x and y change as above. Try to simply, for example, a rotation matrix, right? That's what gives you that equation. So let me know if this is like complete gibberish, but I assume you know how to do a rotation of coordinates. And that's just the xy vector multiplied by the rotation matrix by of an angle epsilon. Alright, so now we've done step 1, right? And step 2 now is to write this when epsilon is very, very small. So we're going to have x prime equals x cos of delta epsilon and y minus y times sine of delta epsilon. And same thing for y prime. So we're going to have cos of delta epsilon and sine of delta epsilon. Let me go to the next page. Oops. So 2, in terms of delta epsilon, we need cosine of delta epsilon. And we also need sine of delta epsilon. So for delta epsilon very small, cos of delta epsilon is equal to, delta epsilon is very small, cosine of delta epsilon is almost equal to 1, right? And sine of delta epsilon is very small, sine of delta epsilon is almost equal to delta epsilon. So I plug that into my equation. Right, I'm plugging it into x prime equals x cos epsilon. So we have x prime is equal to x times cos epsilon, which is 1, minus y times sine epsilon, which is delta epsilon. Similarly, y prime is equal to x sine delta epsilon. So that's x delta epsilon. And then it's plus y cos of epsilon. And cos of epsilon is roughly 1. So x prime is equal to x minus y times delta epsilon. And then y prime is equal to x times delta epsilon plus y. And then z prime is still equal to z, and t prime is still equal to t. So let me just rewrite the y prime one. I'll write it as y plus x delta epsilon. So now we actually have it in a form that we can compare to what we had before. Remember, to get the f and g's, ideally we can write the coordinates as the prime coordinate equals the original coordinate plus something small. times delta epsilon. Or constant. So that allows us to pick out what the f and g's are. So here we can pick out the f, x. So fx is equal to minus y. Right? It's x plus fx delta epsilon gives us x prime. And then similarly here, we can see that fy, it's y plus fy delta epsilon. So fy must equal x. And then z prime is equal to z. So f of z is equal to 0. And t prime is equal to t. So g is equal to 0 as well. So for rotation about the z-axis, we have fx equals minus y, fy equals plus x, fz equals 0, and g equals 0. It's a little bit obscure, especially if you've never done it before. And hopefully you're at least somewhat convinced that I can take any continuous transformation, write down the infinitesimal version of it, and then figure out what the f and g's are that correspond to that transformation. Well, that's really all I need you to believe me, is that it's possible to find f and g's. Right. Now we can move on to the interesting part. Noether's theorem. There's a gap in the notes, actually, if you were reading the typed up notes. It starts off with an introduction to Noether's theorem and then just arrives at the result with no comment. It's because there's a piece of text missing. There used to be a derivation there. It goes from one step to the next. I decided to remove that, but I didn't update the text yet. So Noether's theorem is that any continuous transformation that leaves the action unchanged remember, the action is the integral of the Lagrangian. So any continuous transformation that leaves the action unchanged is associated with a conserved quantity. Just because in classical mechanics we don't like to reuse letters, it's often labeled Q. So if you can identify a continuous transformation that doesn't change the action, then there's some procedure that's going to give you a conserved quantity. We call it Q. So if you want the background, it's called Q because when Noether first derived it, she called the conserved quantity a charge. And that makes sense, right? Because charge, electric charge, for example, is a conserved quantity. And conservation of electric charge actually does come from a symmetry in the Lagrangian for electrodynamics. And so when you consider, and that's sort of the case that she started by considering. She was considering fields, not discrete things like we are. Like we're talking about discrete particles. She was thinking about distributed particles, which we call fields. And so electromagnetism you can think of as a distributed particle, the electric field and whatnot. So when you consider these fields, when you consider symmetries in the Lagrangians, it depends on these fields, you can find conserved quantities. And because in electromagnetism those conserved quantities are charged, once you generalize it to just call it charge. Okay? But it's not literally electric charge. Let's examine a little bit what this means, and then we'll prove it for a simple case. And we'll do the proof for the hard case. So the idea is that if the action is invariant, under a transformation, what we mean is that if you write the action S as some integral in your original coordinates, so from TA to TB of a Lagrangian that depends on your original coordinates, QI, QI dot, and T, that action, if you evaluate everything in the transform coordinates, and I have to go from TA prime to TB prime in the integral, the Lagrangian now depends on QI primed, QI dot primed, and T. The action is unchanged if these two integrals are the same. So you ask, why didn't I change T to T prime in the second integral? So that's because it's a dummy variable of integration, right? So I changed the limits of the integral, but the T that's in the integrand actually doesn't matter, right? Because it's just, it gets integrated out. So that's what we mean by the action being unchanged. And remember, we argued that we can rewrite all of classical mechanics by starting with the principle that the action is stationary. So the action, this integral, really does determine the whole evolution of the system. That's Hamilton's principle. So Hamilton's principle says that making the action stationary gives the equations of motion. So this action is very, very fundamental to the description of the system. And Noether's theorem tells us that if the action is unchanged under a coordinate system, so it's still describing the same system, then there exists a conserved quantity. And this is a prescription for finding the conserved quantity. Now the problem is, how can you dream up of the correct transformation to try to see if the action is unchanged? And that, of course, you can't. But if you can think of one, you can see if it leads to a conserved quantity. Well, in fact, if you do find the symmetry, then it will lead to a conserved quantity. So this is a very general case, right? Here we've done a continuous transformation from the QI's to the QI primes, and then evaluated the action and seen that it's unchanged. Remember, we very specifically chose the case of continuous transformation because it allows us to consider the case of an infinitesimal transformation. If it's true for the full transformation, let's say the transformation is a rotation by an angle, then it's clearly true for a rotation by a much, much smaller angle. So, since this must be satisfied for a continuous transformation, it must also be satisfied by an infinitesimal transformation. So that means that if I write S as the integral TA to TB, again, And the same thing, so our original L that depends on Qi, Qi dot, and T. If it's unchanged under infinitesimal transformation, that means that that's also going to be equal to the integral under the infinitesimal transformation. TA goes to TA plus delta TA. TB goes to TB plus delta TB. In principle, they could be different. Delta TA and delta TB. And then L, instead of depending on Qi, it depends on Qi plus delta Qi. And then Qi dot goes to Qi plus delta Qi dot. And I'm putting a prime in there for no good reason, and you can ignore the primes if you want. The reason that delta Qi is a delta Qi prime instead of a delta Qi, remember in our infinitesimal transformations, we have delta Qi. Qi prime equals Qi plus delta Qi, not Qi plus delta Qi prime. Whereas in Noether's theorem, I put Qi prime. And the reason is that we're considering potentially a variation not just of the Q's but also of T. And since Q prime can depend on Q and T, delta Q could depend on delta, delta Q prime could depend on delta Q and delta T. And that's what this delta Q prime is. It has both the delta Q and the delta T in it. But we're not going to worry about that. So that's just, if you think it's a typo, it's not. It's just obscure. So, back to the main point though. The point is, continuous transformation leaves the action unchanged. For us, the infinitesimal version of that transformation must also leave the action unchanged. And so that's writing the second integral. And so we can write that. We can define, if you want, delta S, the variation of the action, to be the difference in those two integrals, TA plus delta TA and TB. So I'm just doing one integral minus the other. So that's L of Qi plus delta Qi prime, and then we have Qi dot plus delta Qi dot prime, T dt minus the original integral, TA TB, L of Qi dot and T. So Noether's theorem so if a transformation makes delta S equal to 0, then Q is conserved. Where Q, this is the part that's missing in the notes, is how to go from the first line with the two integrals to the definition of Q. So Q is defined as the sum over the degrees of freedom of Pi delta Qi. Now that's delta Qi, not delta Qi prime. So the derivation that you go from one to the other eventually expresses the Qi primes in terms of delta Qi's. So it's that sum plus the second term, the sum from I equals 1 to n of Pi Qi dot minus L delta T. And if I write that in terms of the coefficients of the infinitesimal transformation, that just means I'm writing the delta Qi's, I'm going to call them Fi's again. And then the second term is the sum from I equals 1 to n of Pi Qi dot minus L, and then instead of delta T, I'm going to call it G. Alright, so let's go back. And note this theorem. If a transformation makes delta S equal to 0. Alright, so it's assumed that we have a continuous transformation. So we have a continuous transformation, we can figure out what the f and g's are for that continuous transformation. Alright, so we have that. Now we do the two integrals that we have at the top for delta S. So we calculate the Lagrangian in the transformed coordinates, do the integral and get the action. We calculate the Lagrangian in the untransformed coordinates, do the integral and get the action, subtract the two and find that that's 0. If that's true, so it turns out delta S is 0 because those two integrals didn't matter, so we were transforming the coordinates. So if delta S is true, then there's a conserved quantity called Q, which is given by the sum of the SI times the generalized momentum Ti, plus this other sum, which you recognize as the Jacobi integral, times G. That's quite a lot to absorb, right? So this conserved quantity Q has two terms to it. It has the first term, which depends on the S, so it's related to transformations of the coordinates. Remember, F is the coefficient of the infinitesimal transformation of the coordinates. So this first term depends on the coordinate transformation and somehow involves generalized momentum. The second term involves G. G, remember, is the coefficient for the time transformation. And it multiplies what we've already identified to be the Jacobi integral, which often is equal to the energy. So this conserved quantity, if G is not equal to 0, is related to energy. In fact, you can see that if the G is equal to 1 and the F's are all equal to 0, then the conserved quantity is energy. And so the argument here is that if you have a transformation that leaves the action unchanged, so let's consider a transformation with respect to time. Let's say that the translation in time is just G equals 1, right? And the S are all 0. So under a translation in time, delta S is equal to 0, and the conserved quantity is 1 times the Jacobi integral, so it's energy. So if the action is unchanged by time translation, it's symmetric in time, then energy is conserved. That's sort of a familiar statement that we've heard before, and here is how it is mathematically. And we'll do it explicitly in a minute. Now, this is a very, very powerful statement. And so I didn't prove to you the line that goes from the delta S equals those two integrals to Q equals that sum. But essentially what happens when you do the derivation, you have delta S equals this mess. You use the Euler-Lagrange equation, and then you're going to have in this mess, you're going to have a d by dt of something, and then delta S is equal to 0. So you're going to have d by dt of something equals 0, and that something ends up being the Q. And so we find that when delta S equals 0, d by dt of Q is 0, and so Q is the constant. That's how it is. The derivation itself is a little ugly. Just doesn't add so much. So let's do a more simple example of this with the derivation for a specific case. So the most general case, because of Hamilton's principle, it's the action, the integral, the Lagrangian that controls the system. So if the action is unchanged, then we have a conserved quantity. Now, in most cases, if the Lagrangian is unchanged, then obviously the action is also unchanged. So we can consider the more restrictive case of transformations that leave the Lagrangian unchanged instead of the action. So generally, if delta L equals 0, then delta S equals 0. So we can consider put in parentheses is the more restrictive. So we can consider the case where a transformation leaves L unchanged instead of S. Because I just told you, for S it's actually, the math is a little bit ugly. For L it's actually quite straightforward. So let's consider the case, it's a more restricted case, the transformation that leaves L unchanged instead of S. So there exists, let's say, there exists a transformation, and by transformation I mean one that we can specify the Fi's and the G's. Let's say there exists a transformation that makes delta L equal to 0. So it leaves the Lagrangian unchanged. Alright. And so we have to only consider the case where G is equal to 0. It turns out for the G equals non-zero, you have to do the thing with the action. So our transformation that exists and makes delta L equal to 0 is a transformation where only the F's are non-zero and G is equal to 0. Okay? So our transformation is Qi prime equals Qi plus Fi delta epsilon, and so our delta Qi we define to be Fi delta epsilon. So, given that, consider the variation of the Lagrangian. Remember L is a function of Qi, Qi dot, and T. And we're considering the case with delta T, where T is not varied in the transformation coordinates. So, the variation of the Lagrangian from I is applying the chain rule, since it depends on two different things, right? It's got to be di-L by di-Qi delta Qi plus di-L by di-Qi dot delta Qi dot. Right? I'm just writing the variation of the Lagrangian in terms of the chain rule. So in terms of delta Q and delta Q dot. So from the Euler-Lagrange equation, well, it's not really from the Euler-Lagrange equation, but the definition of generalized momenta is di-L by di-Qi dot. And then from the Euler-Lagrange equation, Pi dot is equal to di-L by di-Qi, right? I have d by dt of di-L by di-Qi dot in the Euler-Lagrange equation minus di-L by di-Qi equals 0. The first term here with the d by dt is Pi dot. And so in the case when Q is not cyclic, for example, then Pi dot is equal to di-L by di-Qi. So I care because I want to put that into our equation. So delta L is sum from I equals 1 to n of, so I have the first term is di L by di Qi. So that term, di L by di Qi is Pi dot. No, I'm sorry. Yes. No, I'm sorry. First term is Pi dot. So it's Pi dot times delta Qi plus the second term is di L by di Qi dot, which is Pi, and then it's delta Qi dot. So that turns out to be the same thing as saying d by dt of the sum from I equals 1 to n of Pi delta Qi. So naively, it's definitely true, right? Because I'm doing d by dt. P and Q both depend on time, right? So I do d by dt and have to do the product rule, so I'm going to get what's above. And it's like, well, is that really correct with these variations? Are you really allowed to do that? And then, yes, you actually are really allowed to do that because we demonstrated that in the first chapter. We looked at the properties of the variation, or the second chapter again. And the variation does commute like that with derivatives. So it is indeed correct. Okay, now if I write this as my delta Qi here, I'm going to write delta Qi is Fi delta epsilon, right? And the delta epsilon is constant. It doesn't depend on which I, right? The Fi part makes a difference for each coordinate, and the delta epsilon is a constant. So I can bring it outside of the sum and then the derivative. And I can write this as delta epsilon times d by dt of the sum from I equals 1 to n of Pi Fi. I'm just going to rewrite the same equation. Oops. So we have delta L. So under the transformation from the Qi to the Qi prime, the variation of the Lagrangian we just saw we can write as delta epsilon times d by dt of the sum from I equals 1 to n of Fi Pi. So you can see where this is going, right? So if the transformation from Qi to Qi prime leaves the Lagrangian unchanged, so that means delta L is equal to 0, then if delta L is equal to 0, then the sum from I equals 1 to n of Fi Pi is equal to a constant. Alright, if delta L equal to 0, then I have delta epsilon times d by dt of the sum is equal to 0. Now if it's equal to 0, then delta epsilon just cancels out. So I have d by dt of the sum is equal to 0. And if d by dt of something is equal to 0, that thing is constant. So what is this term? Well, let's go back up to Noether's theorem. Noether's theorem tells us that if the action is unchanged, then there's a conserved quantity Q that has two terms in it. One is the sum of the Pi Fi, and one is the other sum, the Jacobian integral times g. And so the part that we just derived the first part of that equation. So it turns out if you want to consider transformations in time, you have to do it on the action. But if they're transformations of the coordinates, then you can do it on the Lagrangian. And then you get the first term out. Okay? So this is the first term in Noether's theorem. So remember, Noether's theorem only applies to continuous transformation. Right, so reflection about a mirror, for example, that's not a continuous transformation. So in general, the conserved quantity Q is the first term, and then the second term comes from the time part. So the procedure in general is to figure out what the F and G's are, test to see if the action or the Lagrangian is unchanged, and if indeed it is, then you can figure out what the conserved quantity is. Alright, so now let's go into a few examples. Let's figure out the conserved quantities based on certain transformations. So I'll consider translational symmetry. So for a translation, the transformation equations are that Qi prime is equal to Qi plus Si delta epsilon, where Si is equal to 0 or 1. If you're translating in that direction, then it's, well, I guess it's not 0 or 1, right? Because you can be translating a little bit in one direction and a lot in another. Now let's take that part out. So everybody agrees that that's the transformation equation for a coordinate, the transformation equation for a translation. All right. So we did an example earlier for translation along x. We have fx equals 1, and then fy equals fz equals 0. So suppose L is unchanged by translation. So you figured out one of the translation of coordinates, and if you go in the Lagrangian and you plug in all the translated coordinates, you find a Lagrangian that's the same. And you could have added an overall global constant, but if you just added a constant to the Lagrangian, it's still the same, right? So the variation, delta L, is still 0. All right, so an obvious example of how to find a Lagrangian, to find a translation where the Lagrangian is unchanged by that translation, is if that coordinate doesn't appear on the Lagrangian. Right, so Lagrangian only depends on x and y, then clearly if you translate everything in z, the Lagrangian is unchanged. Right, so it's a very obvious example, right? If the coordinate doesn't appear in the Lagrangian, clearly the Lagrangian is invariant to translations in that coordinate. So that's the same thing as saying that coordinate is cyclic, right? So, but if we don't think about it, and we just plug in now, so suppose L is unchanged by translation, then we know that Q, which is given by the sum from I equals 1 to n of pi fi, is conserved. We don't have the second term, right, because we're not doing any, our transformation doesn't have time in it. We're only considering translation. So in translations, G is equal to 0. All right, so the second term, and if there's conserved quantity, is 0. So for each non-zero fi, we get contribution to Q. So for example, let's say L depends on Z, but not X and Y. So L is invariant when X and Y are translated. So generally, L is invariant under translations where fx is not equal to 0 and fy is not equal to 0. And so in that case, Q is going to be fx px plus fy py. And so we can choose translation in, well no, actually fx, they are equal to 1 or 0. Yes. They have to be equal to 1 or 0. So if it's symmetric under it's invariant under transformation in translation in x and y, then both fx and fy are 1, and the conserved quantity is 1 times px plus 1 times py. The momentum in x and y coordinates. If it's only invariant to translation in x, then only fx is equal to 1, and the conserved quantity is px. So this is the idea that if a system is symmetric under translation, then momentum is conserved. This is the mathematically formal way of saying that. Yeah, so Fi is 0 or 1. Okay, so under translation, you see that momentum is conserved. Do a more complicated one. Do rotational symmetry. So suppose L is unchanged under a rotation about the z-axis. So for a rotation about the z-axis, we've already identified that fx was equal to minus y, fy was equal to plus x, fz was equal to 0, and g was equal to 0. Right? Remember, that's the example we did in the beginning when we introduced continuous transformations. So the conserved quantity is given by sum from I equals 1 to n of pi fi. And so that sum is minus y times px. It's the first term. The second term is plus x times py. And then fz is equal to 0 and g is equal to 0. So the conserved quantity is so minus y px plus x py is conserved. So you have a Lagrangian. Somehow it doesn't depend on the orientation of the x and y axes. You get the same system described either way. If that's true, then you can figure out the fx and the fy and the fz for that transformation, plug them into Nernst's theorem, and get a conserved quantity. And you get this obscure minus y px plus x py that's conserved when a system is rotationally symmetric. So can you tell what that is? This conserved quantity? Let's take the cross product of a vector x hat, so x times x hat plus y times y hat plus z times z hat. And take the cross product of that with a vector that's px in the x hat direction, py in the y hat direction, and pz in the z hat direction. Alright, so that cross product is r cross p, and the z component of that cross product is x py minus y px. And so r cross p, of course, is what we call angular momentum. So it's the angular momentum about the z-axis. That's also very interesting. If a system is rotationally symmetric about an axis, then the angular momentum about that axis is conserved. And you've heard of this, but you've never seen it proven mathematically. that's the statement. And so it's very general. So that's pretty neat as well, right? Let's do one more, and then we're done with all the easy ones. And then, you know, it's going to be system dependent on what the conserved quantities are. The last one we'll do is time symmetry. So we kind of already know the answer. We've done it like 2 or 3 times already. So suppose L is invariant under time translation. Now it's only a time coordinate transformation. So T prime is equal to T plus 1 times delta epsilon. So G is equal to 1 for time translation. So an obvious case of when L is invariant under time translation is if L doesn't actually depend on time. Well, that's a very obvious example. Clearly, if it doesn't depend on time, it's not going to depend on when you change time. So then the conserved quantity is G, which is 1, times the sum from I equals 1 to n of pi dot, pi qi dot minus L. So the sum is only the things with i's in it. And so that, of course, since G equals to 1, that's equal to H, which is the Jacobian interval from the previous chapter. And then often we know that H is equal to E total energy. It's not very good English to say often we know. Let's make it good English. We know that often the Jacobian interval is equal to total energy. There you have it. So when a system is invariant under time translations, energy is conserved. Sometimes it could be that it's not exactly energy, but usually it's energy. So this actually, so we covered the whole chapter in one lecture. So this probably, so it seems like it's not important, but it's probably one of the most important concepts to learn in physics, because a lot of physics is based on this as theorem. Sometimes we find that conserved quantities, so like this, I was telling you the standard model of particle physics, that is a Lagrangian, right? The standard model of particle physics is just a huge Lagrangian. And every term in that model are terms in that Lagrangian are terms that people figured out that mathematically these terms are allowed. And the strange thing is that any term that's been mathematically allowed has turned up in the Lagrangian. There's a couple that we don't know yet if they exist, if they're in nature, but so far it looks like anything that's mathematically allowable ends up in the Lagrangian. Well, given that, people have looked at the Lagrangian and the theorists have time to test various transformations. And so they'll test the transformation and see that the Lagrangian particle physics is unchanged. And so then they conclude that there must be a particle that exists. A conserved charge could be a particle. It could be something else more fundamental. On the flip side, we have other things. We have, for example, in the physics that I work on, neutrinos, we have a a conserved charge for neutrinos and electrons that we call lepton number. So you know there's leptons and fermions. Is that right? Yeah. Bosons. Fermions. Right. So leptons are neutrinos and electrons. And empirically, we verify that lepton number is conserved. So in all the physics that we've observed, we've always seen that the numbers of leptons coming in is always equal to the number of leptons coming out. So we've postulated that lepton number is a conserved quantity. The really weird thing, though, because we've observed that it's conserved, so we've just made a bunch of measurements and it's always conserved. The weird thing with lepton number is there's no symmetry that we can identify that says that that quantity should be conserved. So we say it's accidentally conserved. So it looks like this quantity is accidentally conserved and we don't know why. And so one of the reasons may be, well, maybe it's not actually conserved. And the physics that I do is actually to see if that quantity is not conserved, because there's nothing that tells us it should be conserved. And so a way for lepton number to not be conserved is for neutrinos to be the same as antineutrinos. And so the physics I'm looking for is to see if neutrinos and antineutrinos are really the same thing. And that would imply that lepton number is not conserved. So it's kind of been an overview of the subject here of conservation laws and symmetries, but it's a very deep and very important foundation of modern physics. Any questions? All right, so that'll be the end of the lecture today. I should note that we're going to skip the next chapter in the notes. The next chapter in the notes is the one on applications of the Lagrangian, and I highly encourage you to read that through and make sure you understand it. But we're going to go to the next chapter, which is, I guess, number 7 on Thursday, and we'll start talking about the Hamiltonian, which ties into quantum mechanics. Okay, so Thursday, we'll start with chapter 7. So we're skipping chapter 6. Okay, so if there's no questions, I'll talk to you all on Thursday. Thanks, everyone.